I welcome you all to this 4-week MOOC course on analog electronics, week 3, lecture 2. So we have seen in the previous class the mid-frequency and high-frequency analysis of FET RC coupled amplifier. Now the low-frequency analysis. So in the low-frequency case, again we are dividing into two parts. One is considering inside and output side coupling capacitor is one thing, and a second case is considering only the source bypass capacitance. So first case we are considering and we are seeing the effect of input side and output side coupling capacitor. So concern corresponding equivalent diagram is VS, RV, CC, RG. The voltage across RG will be VGS and dependent current source GM VGS parallel with RD internal resistance, external RD, capacitor coupling capacitor, and RL. So here V0 is equal to minus GMVGS RD dash into RL divided by. So see here RD and RD are parallel and capacitance and load resistor. So dependent current source. See, this combination can be replaced with a Thevenin's equivalent model. So these two are parallel, RD and RD parallel. I am representing it as RD dash. So this voltage source will become GM VGS RD dash. RD dash is RD parallel RD. Then in series with the capacitor and resistor. So V0 is the voltage across the load resistor. The voltage is minus GMVGS RD dash multiplied by load resistance divided by total resistance. Total resistance is RD dash 1 by j omega cc plus RL. I have not taken the in detail diagram here because it was repeated so many times in the previous lectures. This Norton's equivalent is replaced with a Thevenin's equivalent, where the Thevenin's resistance, Norton's resistance, is parallel combination of RD and capital RD. So my V0 is equal to minus GMVGS multiplied by RD dash multiplied by, see, we're taking from the denominator RD dash plus RL as common. So RD dash plus RL. The remaining component is 1 plus 1 by j omega cc RD dash plus RL. So minus GMVGS, this is completely taken as RL dash. It is parallel combination of capital RB, small rb, and load resistance. Then leftover component is written here. Then from the input side equation, VGS is the voltage across the RG resistor. So Vs into RG by RV plus RG plus 1 by j omega cc. So in the denominator, we'll take RG plus RV common. So that will becomes B0 is equal to minus GM Vs into RG by RG plus RV multiplied by RL dash 1 plus 1 by j omega cc into RG plus RV 1 plus 1 by j omega cc into RD dash plus R. And Vs taken this side minus GM RL dash, and this value is 1. So minus GM RL dash divided by 1 minus j. J is taken to numerator, becomes minus j. The leftover component here is F11 divided by F. Similarly, 1 minus j F12 by F. F11 is equal to 1 by 2 by Cc into Rg plus Rv. F12 is equal to 1 by 2 pi Cc Rd dash plus R. So this is the effect of input side coupling capacitor and output side coupling capacitor. Now we'll see the effect of source bypass capacitance next case. Considering the source bypass capacitance. This analysis requires more time, but a very simple analysis. We will take equivalent diagram. VGS is the voltage at this place. GM VGS parallel with RD, and RD dash RL is the combination. So voltage at gate terminal is RVS into RG divided by RG plus RV. And we have taken good number of times this discussion. RG plus RG by RG by RG plus RV is 1. So VG is equal to VS. And output side circuit is replaced with its Thevenin equivalent circuit. So GFVGS parallel with RD is replaced with its Norton equivalent. Voltage source value will be GMVGS into RD in series with RD resistor. So GMVGS RD in series with RD resistor, taking output across the load resistor. Assuming the current flowing through this circuit is ID, taking the equation, total voltage is GMVGS into RD. Current flowing through the circuit is ID. ID into this, I am taking parallel combination of RS and CS as ZS plus RD plus RD parallel R. And VGS is VG minus VS. Already VS is there. That's why I am considering this as VS1. So VGS is equal to VG minus VS. So VS1 is a voltage across the parallel combination of ZS. So VG minus VS1 is, VG is already, we have taken VS here. So VS minus ID into ZS. So making all things more simplified in the next slide. So GMRD. So in this equation, we are making the substitution of VGS. GMRD, VGS is there. In place of VGS, we'll substitute this one. GMRD multiplied by VS minus ID into ZS. Then ID into remaining component as it is. ZS plus RD parallel R. And making this more simplified analysis, making ID, complete ID into one side and getting an equation for drain current. So simplifying this, GMRD VS minus GMRD ID into ZS is equal to ID into ZS plus small rd plus capital RD parallel with RL. So from this ID taken common, the combination is ZS. GMRD is the current amplification factor. So we replace it with mu. So ZS plus RD parallel RL plus mu into ZS is equal to mu Vs. Now we'll get equation for ID. ID is equal to mu Vs by RD plus RD parallel RL plus ZS into 1 plus mu. V0 is the voltage across the load resistor. That load resistor in this case is RD parallel RL. And current direction is opposite. So we are taken minus ID parallel with, minus ID multiplied with RD parallel RL. Substituting ID equation in this. So V0 is equal to minus mu Vs RD parallel RL divided by RD plus RD parallel RL plus ZS into 1 plus mu. So Vs taken towards LHS side, V0 by Vs is equal to minus mu RD parallel RL divided by RD plus RD parallel RL plus ZS into 1 plus mu. More simplification is needed here, right? So mu, we are writing it as a GMRD for more simplification. So minus GMRD, RD parallel RL, RD plus RD parallel RL plus ZS plus we are substituting 1 by J omega C. It's okay. RS is neglected. So into 1 plus mu. Making this a more detailed analysis, minus GM RD parallel RL. Denominator, we have RD plus RD parallel RL taken common and written in the numerator part. So leftover component is here 1 plus the numerator 1 plus mu, denominator j omega j 2 pi f cs. Because we have taken this common, the leftover thing is RD plus RD parallel RL. And this is RD parallel with capital RD parallel with RL, this resistance, which is load resistance RL dash. So AVLF is equal to minus GM into RL dash divided by 1 plus mu divided by J2 pi F CS into RD plus capital RD parallel with RL. So comparing it with the standard equations, you get F13 is equal to standard equations, comparing it with the standard one. This is AVMF and F13 is 1 plus mu divided by 2 pi CS into RD plus RD parallel. This is F13. So overall, we'll say that F11, F12 and F13, three high-pass filters cascaded. The overall lower cutoff frequency is F1 is equal to max of F11 comma F12 comma F13. F21 and F22 discussed in the previous session. Corresponding low-pass filters overall F2 upper cutoff frequency is minimum of F21 comma F22. So that's all for this session. Overall consolidated thing, consolidation of all the results will be shown in the next slide.